All right, back for the next example. Remember, 4 ways flux can change. Change the angle, we just did that. Change the field strength while keeping these other things constant. That's what we're going to look at next. And our example here is to consider a long straight wire carrying a positive current. Notice that the current is changing. As soon as I see that, I think there's going to be a magnetic field that changes as well, since magnetic field is related to current strength. They give us the dimensions of the wire, the resistance, and answer in terms of the given quantities. So what's the magnetic field at a distance from the loop? We did this in Ampere's law in the magnetic unit. Figure out what page you did this in your notebook, Ampere's law, from the magnetic field for a long straight wire. Write that page in here so you can refer back to it if you need. First thing I would do with this, though, before we get too involved with the questions, is think about the situation first, okay? We have a current flowing through a wire, and that's going to create a magnetic field inside this loop. We can use the right-hand rule to determine which direction that is. You would point your thumb in the direction of current, so point your thumb to the right, curl your fingers. Above the wire, up here, if you point your thumb to the right and curl your fingers are pointing out of the page here, right? So we have a magnetic field here, which is going to point out. It exists outside of the loop as well. Right? It would exist down here. It would exist up here, all over the place. It's not going to be uniform. As you get farther away, the magnetic field is going to get weaker. Now, because the current in this wire right here is changing, if we go back and look, how is it changing? This is an exponential decay. It's getting smaller. So the magnetic field here will also be getting smaller. That means this magnetic field is changing, and we have a changing flux inside the loop. Changing flux is going to induce a current. Which way is the current going to be induced? Clockwise or counterclockwise? Well, you use Lenz's law for that. Remember, when the magnetic field decreases, the change in flux is opposite of the magnetic field. So here, the change in flux is into the page because the field is decreasing over time. Now, if you point your thumb in the opposite direction as the change in flux, it's going to point out of the page. And you curl your fingers, and you will get the induced current going counterclockwise here. Okay? So I'm going to draw that in. There, and there. That is our induced current. I induced. Or you could call that IL, like a little L for the loop. Maybe I did that in this example. I don't remember. I'll have to come back and change it if I did. And you can tell that direction is correct because if you curl your fingers around this way, which way does your thumb point? Out of the page. Which way is the magnetic field changing? Into the page. So this would create a magnetic field in here, which would want to oppose the shrink. It wants to keep the magnetic field the same. So if this is getting smaller, you need to add to it out of the page to keep it the same. That's what this current wants to do. Okay, so that's just a conceptual overview. Very good idea to do that in these kind of problems before you get caught up in any of the details. Just understand what's going on. Now, what do we have to do? We have to determine the magnetic field from Ampere's law, determine the net flux, determine the induced current, and the net force. So from last unit, Ampere's law, B equals mu naught I over 2 pi r. R would be the distance away from the loop. And if we substitute in what they gave us for the current, we get this expression. All right, part B. Now, B varies with height, right? Because R here is our distance away. So as you go further up, the magnetic field decreases. And you cannot simply multiply the magnetic field by the area to get the flux because the magnetic field is changing. What we're going to have to do is integrate. So here's kind of the setup, right? Here's our wire with the current flowing to the right. It's up a distance d. This was a height. We had a width. We're going to cut this into little tiny strips and find the flux in each strip and then add up all these strips through integration. So the distance that we are up is r. This little strip has a width or a height difference of dr. So the magnetic flux, start off with the general equation, b dA cosine theta. The angle here is 0 degrees because the magnetic field points out of the page. And the area vector for this would point out of the page as well. Now, who's to say that the area vector doesn't point into the page? Either way, though, you're going to get cosine of 0 or cosine of 180. Both, it's going to be 1 or negative 1. The only difference is a negative sign. And generally speaking, these questions will deal with magnitude. So I plug in for B. dA was W, the width, times dr. And then all of this stuff is constant except for the r. So we get the integral of dr over r, which is going to be an ln, right, natural log, and we evaluate it top and bottom. Now I'm not showing the steps where we plug this in and subtract, but you know when you subtract logarithms, they become a fraction, right? So we end up with this. All of this stuff, there's the ln, there's the fraction, upper limit minus lower limit, so it turned into that fraction, and that is all the magnetic flux. So the next thing we do is use that flux to determine the current. Now, flux is not directly related to current, but the flux will create, the changing flux will create a electric field which around the loop becomes a voltage difference, and the electrons in the loop respond to the electric field, right? They're free to move. Electric field, they will move. So we use I for the loop is epsilon over r, and that's what I had labeled I induced here. That is I of the loop, right? And remember, epsilon here is just a voltage, and that voltage is negative d phi b dt. That's the Faraday's law, right? It's the left side and the far right side of Faraday's law. So we got to take the time derivative of this. Everything here is a constant except e with respect to time. And what do you do when you take the derivative of e to the negative kt? The negative k comes out, cancels with that negative in front, and there is our voltage expression. Kind of long, but not too difficult to take the derivative of it. And then to find the current, you divide the voltage by the resistance. This is not a radius, that's resistance. And we get this. Now part D asks about the forces on the wire. Let's go back up here and examine what the forces would be. Since we have a current moving in a magnetic field, we know there's a magnetic force. That's IL cross B. So we want to find the direction of magnetic force on each side of the loop. So IL cross B. Point your fingers in the direction of I, curl your fingers in the direction of B, and your thumb points in the direction of the force. Again, IL cross B. Current, fingers in the direction of current, curl your fingers in the direction of the magnetic field, thumb points in the direction of the force. So on the right side, over here, point your fingers up, curl your fingers out of the page, your thumb will point to the right. So that's the force magnetic on the right side of the loop. On the top of the loop, point your fingers to the right, curl your fingers out of the page. This one gets, I'm going to make that a little smaller. This one gets a force upwards. On the right, you point your fingers down, you curl your fingers out of the page. This is going to experience a force to the left. And on the bottom of the page, you point your fingers to the right, you curl your fingers out of the page, and this one experiences a force downwards. And I'm actually going to make that a little bigger. Why am I making some of these bigger and smaller? To show you the relative magnitudes. In fact, that one I'm going to make it even smaller. So you can clearly see the bottom one is bigger. Why is the bottom one bigger? Because the magnetic field is stronger at the bottom of the loop and it's weaker at the top of the loop. Okay? So the bottom force will win. The left and right forces cancel by symmetry. The top force upwards is weaker than the bottom force downwards. And we ran out of room for calculations here, so I'm not going to show you all the calculations. But we've done this kind of stuff before. The current in the loop is constant. The magnetic field at the top was not equal to the field at the bottom. The force on the bottom is greater than the force on the top, so the net force is going to be downwards. All right. Next example also deals with a changing magnetic field. And what do we have with this example? This time we have a loop which is at an angle to the magnetic field, but that angle is going to be constant. They tell us some information, the radius, the resistance, the angle, and then they give us the magnetic field as a function of time. What is this doing? It's getting smaller because this term's negative, right? So first question, on the diagram, mark the direction of the induced current in the loop. Let's think about this first, okay? When you have this for your magnetic field, B is getting weaker. That means the change in flux is the opposite direction. Now, you're going to point your thumb opposite of the change in flux, and the change in flux was opposite the direction of B. So your thumb actually goes with B in this case. Okay? Pause as much as you need and convince yourself, re-listen to it. Convince yourself of this stuff because it's really important that you know how to apply these rules. When you curl your fingers, that will be the direction of current. So again, magnetic field here points this way. It is getting smaller, so the change in flux is this way, but we want to point our thumb opposite of that. So the thumb goes with B, curl your fingers, and you can see here that the direction of current is going to be that way. Right? That is I induced in our loop. Now, this is a good explanation here, but it's kind of wordy. So how could you say that a little easier? Well, you can say the current goes counterclockwise when viewed from above, according to Lenz's law, and that induced current creates a B in the loop which will oppose the change in magnetic field. This magnetic field is growing smaller. So the current in the loop wants to create a magnetic field in here, prevents that from changing. If you curl your fingers in this direction, which way is your thumb point? Towards B. But B is getting smaller. A new magnetic field pointing the same way would prevent it from getting smaller. That's the idea. Part B, derive an expression for the magnetic flux through the loop. So, part B. Integral B dot dA, B dA cosine theta. And in this case, B is constant over the area. It's changing in time, but at any one moment in time, the electric field on the left side of the loop is the same as the electric field on the right side of the loop is the same as the, electric field, magnetic. The magnetic fields are constant for any one, no matter where you are in the loop. They change over time, but at any one moment in time, the magnetic field strength at any one spot is constant. So that can come out, as is the angle. So the integral of dA is just going to be the area of the loop, B A cosine theta. Plug in, that's B, pi r squared for the area, cosine theta. And plug in the numbers, I did multiply things through. This would be in Tesla meters squared, that's the units. For part C here, calculate the induced EMF. Now, the induced EMF is going to use Faraday's law. It's going to be the time rate of change of this, and we can use that induced EMF to find a current later on if we needed to. So this is Faraday's law. It's missing the middle term, as will often happen. And a lot of times you're just looking for a magnitude of voltage, right? We can figure out the direction by using Lenz's law, so most of the time you're just going to be concerned with magnitude here. So I didn't show everything, but when you take the time derivative of this, pretty easy, right? This term is a constant, so it cancels. And this term is just t to the first power, so that's it. That negative could cancel with that one. Again, you're just looking for a magnitude here, so that, or you could put it in millivolts if you wanted to. Milli times 10 to the negative third, 1, 2, 3. In part D, calculate the amount of current. You use Ohm's law, V equals IR, but V is epsilon in this case. So if you want to find the current, it's V over R, epsilon over R. And that's what we have, right? That was our voltage, there's our resistance, and we get that many amps at the end. All right, so these two examples showed you how to apply Faraday's law when the magnetic field is changing. I'm going to pause here and pick up with a new video for the next example.